Hello, welcome to this video. Today we're going to look at Wilson's theorem, which states that p minus 1 factorial is congruent to negative 1 mod p if and only if p is prime. So, for this if and only if proof, we have to do two things. Prove that if p is not prime, then this is not true, and if p is prime, then this is true. And it's not that hard to see that if p is indeed not prime, then this is not true. So I'll leave it as like homework exercise for you. Now, let's get on to the actual hard part of showing that if p is prime, then p minus 1 factorial is congruent to negative 1 mod p. So, there's first of all one thing we need to establish, which is for all a between 1 and p minus 1, there exists another b, which is also between 1 and p minus 1, such that we have a times b is congruent to 1 mod p. And of course, p is prime. And I should say that it doesn't just exist, there is one unique b that exists. So keep that in mind. So, what I will do is to show that it doesn't just work for congruent to 1, but for every, there is a unique b like this that when multiplied by a gives a unique, say, r mod p. And we will do that by incorrectly assuming that there are two different b's, such that when multiplied by a give you the same congruence mod p. So we'll assume that we have two numbers, b2 and b1, where b1 is bigger than b2, and they're both between 1 and p minus 1. And it is in such a way, they're chosen in such a way that we have a times b1 is congruent to r mod p, and a times b2 is congruent to the same r mod p. So the first thing we're going to do is to subtract a times b1 from a times b2. And because they're both congruent to r mod p, and that means that when we subtract them, they will be congruent to 0 mod p. So we have a times b1 minus a times b2 is congruent to 0 mod p. Now what that tells us is that p divides into this expression, and I'll take a as a common factor to get that p divides into a times b1 minus b2. But we know that p is prime. So That means that if P divides this multiplication, then P will have to divide either A or B1 minus B2, or both of them. So this tells us that P divides into A, or that P divides into B1 minus B2, which tells us that I'm going to loosen this to get that we have either A bigger than or equal to P, or that B1 minus B2 is bigger than or equal to P. Now, let's look at this. We know that A is smaller than P. We define it as between 1 and P minus 1. And we know that because B1 is bigger than B2, we know that B1 minus B2 will still be smaller than P, because both B1 and B2 are between 1 and P minus 1. So B1 minus B2 is also smaller than P. But here we get our contradiction. So let's clear the board again, and we'll work with that. Okay, now we've shown that for all A between 1 and P minus 1, there is a unique B also between 1 and P minus 1, such that A times B is congruent to 1 mod P. It's really any congruence mod P, but we'll just work with 1 because that's what we need. Now, let's see. So our strategy will be to take every number in the multiplication of P minus 1 factorial, so 1 times 2 all the way on to times P minus 1. Take every number there and multiply it by its own inverse, mod P, which is what we found. So B is the inverse of A mod P. Because of this, A times B congruent to 1 mod P. But there is still something we haven't shown, because there still can be numbers that are their own inverse. So they can't be paired up with their inverse because they only appear once in the multiplication, in the product. So let's just see when A is equal to B and work our way to achieve this inequality. So A times B is congruent to 1 mod P. So if A is equal to B, we have that A times B, which is A squared, being congruent to 1 mod P. But now we can square root this to get that A is congruent to plus or minus 1 mod P. So because A is between 1 and P minus 1, we get that A is equal to 1 or P minus 1. But because those are the only numbers that are their own inverses, this means that for all A between 2 for all A between 2 and P minus 2, there is a unique also between 2 and p minus 2, such that A is different than B, and A times B is congruent to 1 mod P, aka B is A's inverse mod P. Now, what we're going to do is, like I said, pair up each number between 2 and p minus 2 with its own inverse. And because no number in that group is its own inverse, everything will be fine. But now, when imagine pairing up each one, but then multiplying them all together. They will still be congruent to 1 mod p, but because each one has a unique inverse mod p, which is different than itself, we'll have each number appear exactly once in the product. Each number between 2 and p minus 2. So in other words, 2 times 3 times 4 all the way on to p minus 2, and we'll attach a 1 at the end because that doesn't change anything, is congruent to 0, is congruent to 1 mod p. But now, we can see that if we just add another p minus 1 here, we get p minus 1 factorial. So, we have p minus 1 factorial is congruent to p minus 1 mod p. But now, because this is mod p, we can just take away this p and get that this p minus 1 factorial is congruent to negative 1 mod p when p is prime. And that's what we wanted to achieve. So, that's it. And before I end the video, you might think that this can be used maybe as a technique to detect primes, but the truth is, these factorials get so large so quickly, and the numbers that we check for being prime are so big that computers just won't be able to handle their factorial and show that it's congruent to negative 1 mod p or not. And if they can, it will take so much time to actually do it. So if you thought that this can be used as a primality test, it can't. With big enough numbers, it just wouldn't work. So that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more things like this in the future. Finally, that's it.